Good evening and welcome to Monobiology. This evening's lesson is all about the action potential. And this is, as it says in the title there, how an electrochemical signal moves along a neuron. As you folks know, I'm not the best artist. So what I'm going to do, quite simply, is give you an idea of what happens here. I'm going to represent the neuron membrane as a line. This is the outside of the neuron. This is the inside of the neuron. Remember, a neuron's a cell, so this would be the inside of the cell. This would be the outside of the cell. So to begin, neurons always start in this process as a resting membrane. In a resting membrane, there's a difference in charge between the outside of the neuron and the inside of the neuron. This is due to a difference in the number of positive charges inside and outside. As you can see in the picture here, there are a greater number of positive charges on the outside than there are on the inside. So because there's a greater number of positive charges on the outside, we say the outside is positive, and there's a lesser number of positive charges on the inside, so we say the inside is negative. It's not really negative, it's just negative with respect to the outside. Now we're going to figure out how the cell creates that difference in charge. But remember, just like in photosynthesis and cellular respiration, what we've done here is we've created a potential energy gradient. Okay, so in other words, there's a bunch of positives out here. Where do they want to go? Diffusion says they want to go into the cell. And because they can't, there's potential energy stored in that. The cell is going to use that potential energy to do work later on. So how does the neuron create this difference in charge? The difference in charge is created quite simply because the cell membrane becomes more permeable to potassium ions than to sodium ions. For every 2 potassium ions that diffuse into the cell, only 3 sodium ions diffused out of the cell. Because of this, the outside of the cell becomes more positively charged. Typo there, should be becomes more positively charged. Okay, so you've got 2 potassium ions going out, 3 sodiums, correct that again, 2 potassium ions going in, and 3 sodium ions coming out. You can see for every 2 that are going in, 3 are coming out. That's going to create a very positive charge on the outside of the cell. Now how this happens is because of the sodium-potassium pump, which we discussed earlier in the course. And as you know, the sodium-potassium pump requires energy to do its job. So it's a form of active transport. So in order for this whole process to work, the cell has to use energy. It has to use energy to have stored energy on the outside of the cell. Okay, so the outside of the cell has a higher positive, inside has a lower positive. That is your resting membrane. This is called the resting membrane, and it's said to be polarized because of the difference in charge. Now we're going to talk about what happens when the neuron becomes stimulated. When a neuron gets stimulated, we say it gets excited. Same kind of idea, neuron stimulated, excited. When a neuron becomes stimulated by either the brain or by a sensory cell, the cell membrane of the neuron becomes depolarized. Okay, so we start off with a membrane being polarized. When it gets excited, it becomes depolarized. In order for a neuron to become depolarized, there has to be a reversal of charges across the cell membrane. In other words, the inside of the cell becomes, again with the typo, becomes more positive and the outside of the cell becomes more negative. Okay, in reality what happens here is that there's gates on the cell membrane that let only sodium in. So when depolarization occurs, when the neuron gets excited, those sodium gates open, sodium rushes into the cell, reversing the charge. And that is the depolarized membrane. Now once depolarization occurs in one location on the membrane of the neuron, it will continue until it gets all the way to the other end of the neuron. Now, if you look at your neuron, this would start in the dendrite and finish in the axon. Okay, so key here is depolarization, reversal of charge. How does the action potential travel down the neuron? Well, if you look at the picture we have here, again, I know my artistry is not very good, but you guys get the idea. We have the outside of the cell, the inside of the cell. Okay, so depolarization moves along in this way. Okay, so this one originally, if we break apart the membrane into sections, which, just for the sake of showing how it works, obviously it wouldn't really look like that in real life, but if we break it apart into sections, this would have been the first section to be depolarized. This section is now depolarized, and this section is now depolarized. Once a section has become depolarized and the signal continues to move along, repolarization occurs. And that's basically where it goes back to the resting potential. Okay, so the resting membrane becomes depolarized. Then the next section of the membrane becomes depolarized, while the next section of the membrane becomes depolarized. But remember, as soon as the signal has been passed on, repolarization has to occur. And again, the sodium-potassium pump does that work. Okay, so that, in a nutshell, very basic idea here is how an action potential, a signal that goes through a neuron, travels from one end of the neuron to the other, and how it works. Make sure you take notes on this, and also make sure you bring your questions to class. To finish up this little lesson, I need you also to start with number 1. It's a little shorter. Start with number 1 and have a listen to it and add to your notes. Okay, so we've got three sections. We've got polarized, depolarized, and repolarized. You can add to your notes there. And then I would also recommend this YouTube video, which, I do a good job of explaining it, but my pictures leave something to the imagination. So if you want to see what it really would look like, these are some good animations here, and they do a little bit. They explain a little bit too, but not as good as me, of course. Good evening.